Okay, hello people. Welcome back to the corgi64 project where we're building a virtual computer from scratch. Last time we implemented the flags register, and what we're going to do is we're actually going to fix up that name a little bit, and instead of using this camel case, we're going to have snake case. So we're going to search here for everywhere there is the set arithmetic flag, and we're going to say it's going to be set arithmetic flag, and we'll just replace all those, and there we go. So that's the first thing that we're going to do. So the next thing that we're going to do today is we're going to start on those jump instructions. So now that we have a arithmetic flag, or our flags register taken care of, for now we're going to do a jump instruction. So let's go over here to our document, and let's see, where do we want to do? We want to have a jump. Maybe we'll have an unconditional jump. Maybe that's what we'll do. We'll implement that first. So we'll implement the JMP function. So let's go back to our CPU.h file and go down here, memory opcodes. Let's have our let's create a jump opcodes section, and we'll say okay, void jump. We'll give it our CPU, and then what we're going to do is this is, let's see, an unconditional jump. So what's it? It's going to have an unconditional jump to a particular destination, which means that we are going to have to get the value from our instruction register. So we'll say that we want, let's see, we're actually going to be, let's take a look at our CPU. We're going to want to update our program counter, which is the PC, with the value in our instruction. So let's see, so we're going to have our instruction there. So let's go ahead and do that. So our CPU program counter will be updated to have the value, the I64 value of our C, let's see, instruction, whoops, value. And that should allow us to jump. Yeah, that should be it. So what we're going to do is we need to write a little test for this. So let's go over here and let's say test jump opcodes, and we're going to have a test JMP, and we'll give it our CPU. And then we'll have to write our test, so we'll say void test jump CPU, and what we're going to do is, let's see, we probably should, let's see, if we're going to have, we actually probably should clear out our CPU. So if we say, yeah, so let's reset our CPU. We'll reset our CPU, and then what we're going to do is we need to give it, we need to set our instruction. So C instruction value, and we'll set it with some number that we're going to jump to, right? So we're going to say, we're going to set the value to, say, 30, and what we need to do is we need to set our program counter to some other value. It doesn't matter what it is. We'll say 1, and then what we can do is we can actually call our jump function with our CPU, and then we can assert that 30 equals our C instruction value. In fact, if we go back over here, do we need C instruction value? You know what? This doesn't even need to be casted at all. It's going to already be an I64, and program counter is going to be an I64, so we should be good. So let's go back to our tests, and we will assert that and do CPU print status. Okay, so let's see if that works. We should be able to build test, right? And that works. So let's do, let's see where we go. It needs to be bin tests. Or wait, is that what we need to do? Let's see. Bin, oh, bin test. There we go. All right, so it looks like all our tests passed, and our program counter is now 30. That's very good. That's very good. So that's very good for that jump. So let's do one more, because we're doing this fairly quickly. So we have an unconditional jump. Why don't we do, let's see, jump to subroutine. Let's see, the jump to subroutine, that'll be an interesting one to do, but probably not yet. Let's branch if the 0 flag is set. So let's branch on equal, so BEQ. Let's try that. So let's go back over here to our jump codes. We'll do void branch if equal to 0. We'll give it our CPU, whoops. And our program counter will be updated again with, let's see, then what we need to do is we need to compare if, no, actually we have our flags, right? So we have our flags system. So how did we set up our flags? Let's go back to our design document. Okay, so the flag summary. So if bit 0 is set, then it will be equal to 0. If bit 1 is set, it's negative. Okay, that's very good. So what we need to do is we need to check our flags register, and let's see, do we want to write a function that will give us a, say, true or false for that? Maybe, let's see, CPU fetch. So here's our CPU, here's our flags register. Essentially, if bit 0, yeah, maybe we do want to do that. So what we'll want to do is we'll want to say, let's create a function that will actually retrieve the value of the flag that we want, right? So let's go ahead and do that. So in our CPU, let's go up here, and I'm not sure where we want to put this function right now, but let's put it up here. So we'll put it up here with the rest of our set. We can get rid of this to do because we already did that. So we have this no up, we've got a halt, print status. Let's do a function here where actually we're going to return an I64, and what we're going to do is we're going to do get flag value. And what we're going to do is we're going to pass our CPU in here, and then we also want to get the flag index. So we'll say int flag index. And what we'll do here is we'll get the value. So we'll get an I64 value. And we may clean this up a little bit later. This will be flags. Right? I believe that's what we call it. Yep, flags. So we've got our flags register in this value, right? We want to have we also want to have an I64 mask, right? And this mask will give us a way to retrieve just the bit that we want, right? So the mask will start out as 1, and it will be shifted over by the flag index. So that will give us a 1, so we'll have all zeros. So let's say our flag index, say flag index equals 2. Then what will happen is, say that we just have 1 byte, 1, 2, 3, 4, 5, 6, 7, 8. So you've got 8 bits here. If we set our flag index, what this mask will do is it will shift. We start out with a 1, and it gets shifted over to positions. So 1, 2. So it should be over here, right? So we get 1, and we shift it over by, say, 2 positions, and that should give us to 1, 2. That should give us get us to a 4 or something like that, right? So it'll give us this second position. I think if I counted correctly, hopefully that's how it behaves. So this gives us our mask, right? And then we'll get a value out of it. And the value, what we'll do with that is we will binary AND it with the mask. And so what this does is if there's any other ones, there may be multiple flags set, right? I mean, right now we only have 2 different flags, but say that there's lots of different flags that we have set. We're only interested in one of them, right? And so what this will do is when we binary AND 2 values together, only the ones that have both have 1s in them will be returned. So this mask actually allows us to single out a single bit. And then what we want to do is we have that index that we had. We want to return it back, right, by that flag index. We want to move it over. So let's say that we had 1, 2, 3, 4, 5, 6, 7, 8. So what we did is we had this 1, which was this number right here. And then we moved it over by the flag index, so we moved it 1, 2, and there is our flag. And then let's say that we had this is the mask, right, and this is the flag, and let's say the flag has, you know, all kinds of weird stuff in there. So we've got all kinds of 1s and 0s and things like that. What will happen is the value will only things that have both 1s in them, right? So only these have both 1s. Well, if both those have 1s, then we'll get a 1. Otherwise, if there's a 0 and a 0, or a 0 and a 1, or a 1 and a 0, then we'll get 0 out. So this will be 0, 0, 0, 0, 1, 0, 0, right? So now our value is this, right? So now we've got that value out, right? And if, like, let's say our flag was 0, right, then this would be 0, right? Okay, so this is what we've got right now. So then what we can do is by shifting it over, see over here, we're doing a shift, and by shifting it over by the flag index, what we end up doing is our value ends up becoming 0, 0, 0, 0, 1, right? So because we can shift this over by 2, and this will end up being 1, and then we can return that, and that will essentially be our 1, or a true value. We can say that, you know, our flag value is set to 1, right? And if it ends up, if our flag was 0, then this would be 0, and of course if we shift a 0 over, we would have 0 as the output. So that's how our flag and mask works. And really what we can do is we don't even need this. We can just return the value. We can return our flags binary ANDed with the mask, and then shift it over by the flag index, and that should be good, right? So that will allow us to get our flag value. Hopefully that works. In fact, let's write a test for it. So let's go perhaps up to the top. So this is the test halt. Let's do void test get what did we call it? Get flag value, right? Test get flag value, and we'll give it with our CPU and flag. Oh wait, this is just testing, so here. So what we'll do is we'll just make sure that our CPU is set to, zeroed out, and then what we'll do is we'll get the flags register, and what we'll do is we'll set flags to 2, and remember for byte-wise, 2 is this, right? So it's a 0 and 1. And of course, in our flags register has 64 bits, so you'd have 64 different values along here. So what we're going to do is we're going to say, okay, let's get flag value. So get flag value, and we're going to give it our CPU, and we're going to say, okay, we want the first bit, right? Because we don't want the 0th bit, we want the first bit. And we're going to have an I64. It'll be the value, and we're going to say, okay, that's our value. We're going to assert that that this value is 1, and we're going to CPU print status, and we'll give it our CPU. Let's see if this works. Let's do a test get flag value. Copy that. We'll put that down here. Test get flag value. So hopefully if this behaves properly, then everything should be passed, so we can go build our tests. Oh, we have a little bit of a problem, so let's see what we're doing here. So it looks like CPU line 128, we have a syntax error. It's probably something, 128. It's down over here. Oh, that's right, we never finished our BEQ, our branch of equal, so let's just get rid of that for now. We'll do a build test. Let's see, what do we got now? Test CPP16, there's an undeclared identifier C, so let's go in our tests up here to line 16, reset C. Oh yeah, that's right, we do need to give it our CPU. Okay, that's very good. Let's see, what else do we need? Test get flag value function does not take 0 arguments. Oh yeah, that's right. We've got to go down to our int main, and we need to give it our C, our CPU. And then if we run that, we get that out. And then let's run our tests. And it looks like all tests pass. If we go up to near the top where our first thing is, we get flags. Yeah, flags equals a 2 value. That's very good. So so that worked. So now we can go back to our branch of equal, and what we'll do is we'll say our program counter will equal get flag value of our CPU and the index. We're actually looking for the 0th one. Oh, and we're not going to be setting our PC counter. What we need to do is we need to have a check, right? So we need to say if this equals 0, then what we can do, right? If it equals 0, then we branch, right? So that's what we want to do. So let's go ahead and branch, and we'll branch by setting the program counter equal to the instruction value, right? So that will be our branch, and what we'll do is we'll set up a test for that. So we'll let's see, where's our tests for branch? Oh, this is our test for branching, right? So maybe I should put a comment in there, tests. Okay, tests for branching. Really what it should do is I should actually break this up. Maybe we'll do the next time. We'll break this up into a couple different files, which will allow us to have a little bit shorter file than having just a file that goes on forever. So let's do a test branch if equal to, and we'll give it a CPU, and we'll reset our CPU, and we'll set our instruction value to some number, say 10. We're going to set our program counter to some value, say 5. And then what we're going to do is, let's see. So branch of equal, did I write this correctly? Okay, the flag value. Okay, so we need to set our flags. So let's say flags. Let's see, so we're going to say, oh, you know what? It doesn't need to be 0. It actually needs to be 1. So if that flag is set, right, if it is 0, the result of whatever operation that set our flag, if that bit is set, if the 0 flag is set, then we will do set our instruction value. So let's go ahead and do that. Instruction value be 10, so flags, program counter. So our program counter in the end should end up being 10, right? If we set our flags, so if we set the flags equal to 1, all right, that means our 0th bit will be set to 1. Then what we can do is we can branch if equal on our CPU with the 0th bit, and then we can assert that 10 will equal the CPU program counter. And then what we'll do is we'll do CPU print status. We may just end up taking out all these print status stuff at the end. So we can build our tests, right? BEQ does not take 2 arguments. Oh, that's right. It just takes a CPU, which makes sense. So we build it, it builds, and then we run it. All tests have passed. And at the very end here, our CPU, shouldn't it be 10? It shouldn't be 30. Let's see. Oh, you know what? We never used our test, so let's do that. So let's go down here to the bottom. We tested our jump, test the BEQ, and we'll build, we'll run. There we go. So now our program counter went from 5 to 10. That's very good. So now we know that that works. So we've already, let's see, we fixed up. As a recap, I think that'll be good for today. As a recap, we created this get flag value. We updated to make sure that we updated the name of our set arithmetic flag to be consistent with the snake case that we've been using. We used our get flag value in our new BEQ or branch equals, and we also created an unconditional jump, and we created some tests for that. So next time we should be able to hopefully finish up our jump instructions, and we'll get that much closer to a finished system. Oh, probably the one other thing that we want to do is we also want to add these opcodes to our opcode table. So let's go ahead and do that. Let's find out where jump and BEQ are in our CPU design. So if we scroll down here in our design text, BEQ is at 2.4. So let's go ahead and do that. So 2.4 BEQ, and then our unconditional jump is at 2B. So let's go over here, and we can go to 2B, and we've got JMP, and that sets that up. We probably also need to set these memory offsets, right? So the unconditional jump both the unconditional jump and the BEQ will have an offset of 9. So both 2.4 and 2b will have 9s. So 2.4 will have a 9, and 2b will have a 9. All right, so I think that actually is good for now. So next time, hopefully we'll finish up some of these jump instructions, and then we'll just have, a few other, maybe implement these bitwise functions, and then once we get the instructions working for our CPU, we can actually start working on other parts of our virtual computer. I think that our next one that we'll work on is probably the virtual monitor, so a screen. So we're going to actually write a virtual screen for our system. Thank you for watching, guys. Till next time.